Welcome everybody to a little bit of calculus here. We're going to talk today. The fourth lesson in this series is on continuity, and just a little bit. I want to clear the air about a couple of things. Like in your pre-calc class, you might have seen, maybe you talked about if something had a hole, then you said it wasn't continuous, or if there was like say a vertical asymptote of some sort involved, you'd say it wasn't continuous. Or the old idea that if you have to pick up your pencil to draw it, you'd say it's not continuous. I want to go beyond those definitions and into like the formal, the calculus, the limit-based definitions of it. So those work fine to a point, but I'm looking for something a little bit more substantive. So when we talk about continuity in calculus, a function f(x) is said to be continuous at some value x equals c. And again, the value of c may change based on different problems, different situations, but there's three conditions that have to be satisfied. Criteria number one, the limit as x approaches that value of c, whatever it might be, of the function f(x) must be defined. Secondly, again, for number one, that means, your left limit has to equal your right limit at c. Number two, f of c has to exist. That's when you can plug into a function and you get a value or a solid dot on a graph. That's kind of what I'm looking at. And then thirdly, not only does this exist and this exist, but they must equal each other. So whatever you find for criteria 1 in your limit must equal what I get from plugging in. So those are the three criteria we're going to play with today. So let's go ahead and do that. In number one, I give you four functions, graphs of four functions. I am telling you right now that all four of them are not continuous at that value c. And you say, well, what's c? Don't stress about that. Could it be 1, 2, 3, 4, 5, like 6? Maybe. Could it be 7? Could it be -3? The value of c in these cases, it can vary. So don't get so upset about what is c? What is c? Depending on the problem, it could be different. So again, let's take a look at our three criteria here. Again, I write them again because the more you write them, the more you experience them, the better off you're going to be. So I know I need the limit as x approaches c of my function f of x. And again, the function could change also. Maybe it's a g of x and h of x, whatever like that. But so I look here. Here is my left limit. It reaches me that hole right here. There's my right limit. It hits me on that hole. So does the limit exist? Yeah, left side equals right side. At x equals c, we're good. Criteria number two. Does f of c exist, or is it defined? And on a graph, I'm looking for a solid dot of some sort, and gotta be honest, I'm not seeing it. So this one crashes and burns because of criteria number two. So I can say, and I'm going to go over just a generic write-up for this. If I were asked to write up, or to justify my findings, I would say that f of x is not continuous. I'm going to abbreviate continuous, CONT, at x equals this value c right here, because f of c DNE does not exist. And that works. Okay? Let's go into the next one. Here's my left limit at this hole right here. Here's my right limit at that dot. Does my left limit and my right limit, do they give me the same value? Quite frankly, the answer to that question is no. One has a y value up here, one has down there. So this one doesn't even make it past the first phrase here. So I'm not even going to worry about whether f of c exists or not. Well, it does. I've got this solid dot right there, but that's all I needed. If one of the criteria fails, the whole thing fails. So I would say f of x is not continuous at x equals c. That's a really awful at symbol, because limit as x approaches c of f of x does not exist. Please make sure anytime you write like a limit that immediately afterwards you write what function it is you're finding, because, you know, could I be talking about a function g of x, h of x, whatever. So that is important to write. Okay. If you want to pause your video for a couple minutes here and take a shot at this and see what happens, be my guest. Otherwise, I'm going to go ahead and explain. If you do pause it, come on back after you tried it and we'll go through it. Again, I'm looking at criteria 1 here. Does my limit exist? What I see here from the left side and the right side is that this function increases without bound. In most of the calculus world, or well, some people would say, well, that means the limit's infinity. Others would say that it does not exist. I'm on team does not exist, so I would say that f of x is not continuous at x equals c, because limit as x approaches c of f of x does not exist. Now, if, you know, maybe the textbook that your professor or your teacher is having you use, maybe instead of calling this a non-existent limit that increases without bound, maybe they call it infinity and say, well, see the left side and the right side, they both go infinity. Okay, this function is still not continuous for this reason, because even if you say, well, my limit goes up to infinity on both sides, here's the value of f of c, and it's not the same, so still not continuous. Last one. Does my limit exist? Yeah, right there where that hole is. So we're good on criteria 1. Does f of c exist? Yeah, I got a dot right there. Good there too. So that means it's continuous? No. Does the value that I get for the limit equal the value of the function when you substitute? So are these the same y value? And that's no. So in this case, f of x is not continuous at x equals c, because the limit as x approaches c of the function f of x is not equal to f of c. So if you're one of those that paused for a little bit and then came back, how'd you do? I hope it went well. Okay, that's the graphical perspective. Let's look at equation perspective here. And in this case, what's happening is that you'll notice your equations are all piecewise functions that I'm going to be giving you for quite a while here. I do that because it is quite frequent on the AP test that continuity is tested with piecewise functions, so that's something I wanted to follow that same kind of format. So I've given you in example 2 a function p of x, and you're being asked to find the left limit, the right limit, the two-sided limit, and the value of the function at p equals 6. So let's go ahead and dig into it and then answer the question. We're going to determine whether or not it's continuous at x equals 6. So here's what I want you to understand. If I am doing the limit from the left at x equals 6, I'm looking for numbers like, 5.99999, and so on and so on. I want something smaller than 6, but yet close. So instead of going and looking at all these functions, I'm going to choose to look at the domain values first. So what I see right here, like that 5.99999, which is my left limit, those are values less than 6. So this equation is giving me my limit as x approaches 6 of the left of, in this case, my function is p of x. So I'm going to go ahead and plug in that 6 into the function that corresponds with that domain that's less than 6. So I got 6 squared minus 4 by 6 minus 2. So I get a left limit of 36 minus 24 is 12 minus 2. That's 10. So good enough. Let me go ahead and do this number. Now again, if I'm looking for a limit on the right at x equals 6, I'm looking for something slightly bigger but yet close to 6, like 6.0000 whatever, 1. So I'm looking for numbers bigger than 6, which is where this middle term, this third graph comes into play. So I'm going to plug into there. So this is my limit as x approaches 6 from the right of the function p of x, which is the absolute value of -2 times 6 plus 2. And let's figure that out in our heads here. -2 by 6 is -12, plus 2 is -10. You say, oh, that's not the same here. Well, it's an absolute value, which means how far is, here's 0, how far is -10 from 0? That is a distance of 10. So since my left limit and my right limit at 6 both give me that value 10, I can tell you that my two-sided limit as x approaches 6 of the function p of x is also 10. So we have satisfied criteria 1. Does the limit as x approaches c exist? Yeah, and the value of c in this case is 6. So then what about finding f of c? Or instead of calling it f of c, I'm going to gear it towards this particular situation and call it p of 6. Well, that's when I want the function to equal it. So this is the value right here, x equals 6, I'm going to use to find my value. So I'm going to take -3 times 6 and add 8. That's -18 plus 8. That is -10. So, does my limit exist? Check. Does p of 6 exist? Check. Are they the same value? No. So, that leads us to that p of x is not continuous at x equals 6 because the limit as x approaches 6 of p of x is not equal to p of 6. And these are generally how you're going to want your write-ups to look for a problem like these. Again, so don't just do the algebra and say that's good enough. This part is equally as important, if not more so. Justifying your findings, that's putting all the algebra you just did into play here, kind of getting all your eggs in one basket here, putting it all together, and then telling what you found. Okay, example 3. Given the piecewise function defined below for g of x, again, I want limit left, limit right, two-sided limit, and the value of g of -2, and then we'll use all that information to determine continuity. Now again, we're talking about -2, so on a number line, here's 0, here's -2, so I need something on the left, something on the right. Again, something on the left is like -2.001, which is something less than, and it appears as if I made a boo-boo on my thing here, because that should not be less than or equal, because I've got equality covered there. So let's make that first one just equality, okay? So then, what am I looking for my left limit? I am looking for things that are less than. So this function will give me my left limit. So let's do the algebra and write it up nice and pretty here. So my limit as x approaches -2 from the left of the function g of x will be substituted into this value. So we get 3 by negative 2 squared plus 5 by negative 2 plus 4. So negative 2 squared is 4 times 3 is 12. 5 times negative 2 is negative 10. So 12 minus 10 is negative, 12 minus 10 is 2 plus 4. That gives me a value of 6. Let's do our right limit. So I need numbers bigger than negative 2. So my limit as x approaches negative 2 from the right of g of x. And here's where I got bigger than, so that is my right limit. And the function I plug into is, well, I don't. It tells me my limit from the left is just 6. There's nothing to plug into. So left limit 6, right limit is 6. My two-sided limit of g of x at 2 is also 6. So, criteria 1, does my limit exist? Check. Next thing I have to find is my g of negative 2. That's when I'm looking for equals. So this is when I find my g of c. And I'm just going to plug on in there, and 2, I'm going to plug into that middle equation because that's where the domain matches up. That is negative 4 plus 10, 6. So, criteria 1, does my limit exist? Check. Criteria 2, does like f of whatever or g of c exist? Check. Criteria 3, is the limit the same as the value that you get from substituting in? Check on all 3 fronts. So what does that mean? Well, it means that function g of x is actually continuous at x equals 6. So I'm going to write it up, and I'm going to justify it. So I can tell you g of x is continuous at x equals 6 because the limit as x approaches 6 of g of x exists. G of 6 exists. And the limit as x approaches 6 of g of x is equal to g of 6. And we're done there. So like a lot of them I've done so far is it's not continuous, it's not continuous. This is how I would justify a continuous. Number 4. Given the piecewise function for fx below, and again we're concerned with the value 4, left, right, two-sided limit, and f of 4. Let's do the same thing. Now, this one, when it's greater than 4, I know is my right limit. This one has a less than 4, which I know is my left limit. But it also has this equality symbol underneath it, which means this one function up above does my left limit and also my value of f of c or f of 4. So I can tell you without, really straining the brain on this one that my left limit and my value of f of 4 are going to be the same thing because I'm plugging into the same value. So I'm going to go, here's my limit as x approaches 4 from the left of f of x. And since I'm substituting into the same function, I'm also finding f of 4 at the same time. So that makes 4 cubed minus 10 times 4 plus 1. That's 64 minus 40 is 24. That's 25. Then I'm going to use my second function, which is the limit 4 from the right. So I plug in 4, I get 6 by 4 plus 7, that's 31. So does my left limit equal my right? Last time I checked, 25 was not equal to 31, or if you do believe that that is true, do me a favor. I'll give you $25. You give me 31. We'll call it even. No, these are not equal. So no, and no money's going to trade hands in this deal. So I know that this is not continuous. So if the left limit does not equal the right limit, that means the two-sided limit exists. So criteria 1 is where this function fails. So I know that fx is not continuous at x equals 4 because the limit at 4 of f of x does not exist. Hoping this is making some sense to you. I've got just a couple more problems here to play with you on. So let's go ahead and do just that. Here's something a little different. This is kind of common on like your AP tests also. Here I want you to find the value of p. You say, well, what's p? Well, p is this parameter right there, meaning I want my function h of x to be continuous at 3. So it's not a case of does the limit exist, does f of whatever exist, and are they the same? It's a they are. All three conditions are met. When I say it's continuous, I'm saying that all three of those things have to be true. The problem is, in order to make it true, I'm going to have to find some value of p here that makes that true. So again, I look at my domain, less than 2, that's my limit from the left. Greater than 2, that's my limit from the right. And since it has the equals there also, that is also my value of h of 3. So as I work the top equation, I basically find my limit from the left. And again, since I'm not asking you to like justify or whatever, I'm going to get, okay, probably a little sloppy in my notation, but I'm looking at more the algebra here rather than a write-up because I'm just looking to find a value. So my left limit is going to be found from the first one. I'm going to replace the x's with 3's. So that's 9 minus 12 plus 8. That's negative 3 plus 8. That's 5. So that's my left limit. So that's my limit. X approaches 3 from the left. hx gives me 5. So then my limit, x approaches 3 from the right of h of x and also h of 3. I'm going to find that by plugging into this second equation. So it's 2 times p, and the value of x we're concerned with in my rule to determine which rule I'm going to use is 3 minus 37, which gives me 6p minus 37. So are they the same? Are they not the same? Well, when I say it must be continuous, what that means is I want them to be the same. So to finish this, really all I'm going to do is to take the 6p minus 37 I got from the first, or from the second equation, and set it equal to my left limit that I got from the first equation. Move the negative 37 over by adding, so I get 6p is 42, divide by 6, and p is 7. So when this parameter right here that I've circled in blue, when that equals 7, that will guarantee that everything is continuous. Okay. Let's throw in a little trig just because we can. Again, I want you to discuss the continuity. Is it continuous? Is it not continuous? At pi over 2. And yes, I do want a formal write-up. So, again, less than, that's going to be my left limit. Greater than, that's going to be my right limit. Equal to, that's going to be my f of c, or in this case, that's going to be my g of pi over 2. And if this is to be continuous, all three of those need to equal the same value. So I'm going to look at my limit as x approaches pi over 2 from the left of g of x. It says sine squared x plus cosine squared x. If you wish to plug in pi over 2 and evaluate it that way, I know sine of pi over 2 is 1, the cosine is 0, and you can go ahead and do that thing. I'm not going to do that because I remember a little thing from my pre-calc class called Pythagorean identities, and specifically I remember that sine squared plus cosine squared is 1. So I can actually find that using a definition or an identity from pre-cal. I don't have to do anything funky. Okay, let's look for our right limit. My limit as x approaches pi over 2 from the right of g of x is cosine of x, or cosine of pi over 2. Now, I'm hoping you're pretty good at your unit circle. I know that's 0. If you don't, there's a couple of ways you can do this. You can go this route. I can make a graph. I know that cosine starts at 1. And then here's pi. There's 2 pi. I'm just going to make a quick sketch. Pi over 2 is 0. Pi is negative 1. 0 and back to 1. So here's pi over 2. That's 0. And I get a 0 and a 1 for my two limits. They are not equal. So I can tell you right now that my function g of x is not continuous at x equals pi over 2 because the limit as x approaches pi over 2 of g of x does not exist. You say, well, you didn't even plug into the other equation. I can, but it's kind of senseless. It just wastes time. Once my limit crashed, nothing else really mattered. So, but, just for the sake of algebra, let's go ahead and find g of negative 2. So, that says 2x, and x approaches pi over 2, all over pi. 2's cancel. I get pi over pi, which is 1. So, g of pi over 2 is 1, which is the same as the left limit, but they do not agree with the right limit, and all three have to be the same. So that one's not happening. Okay, last problems. Take a look at the criteria if you want. If you want to pause the video and try to draw some on your own, you can. I'll just go through some options you could do. Criteria A, I've given you that the limit at negative 2 exists. So here's negative 2. I'm going to put a hole here. Left side, right side are both the same. There's my y and my x-axis. So that definitely satisfied the limit existing, but it is not continuous. Well, this would definitely not be continuous because it does not have even a value for like f of negative 2, so that would bust it. Or if you felt the need to, I could actually make f of negative 2 exist, but since it's not the same location as the hole, you're okay there too. So either like that or like that. In either case, your function is not continuous at negative 2. F of 3 exists, so that means here's y, here's x. 1, 2, 3. It means I need a dot somewhere at 3 comma something, and it has to be a solid dot for f of 3 to exist. But f is not continuous. I mean, I could draw some vertical asymptote and then the dot on there, or probably the easiest way would just say, okay, here's my right limit, pick something else, and then go a left limit that's different. Please do not put 2 shaded in circles because that's going to make it not a function. You're violating functionality here, completely butchering the vertical line test. So when you're going like that vertically, 1 solid dot, 1 hole, and my left limit does not equal my right limit. So that satisfies B pretty easily. And then part C, here's y, here's x. I need the limit at 1 to exist, so I'm going to put a hole. F of 1 to exist, well, could I just put a dot there? That would make both the limit and f of 1 exist, but I need it to be not continuous. So in this case, that's not going to work, because if I fill in that hole, it is continuous, so I'm going to go ahead and just put a dot right there. So I have a limit at this hole. I have an f of 1 at that dot right there, but they're not the same. So those are just a few examples of ways you could draw these. I thank you for your time. I hope I was able to help you and explain the topic of continuity with you, and happy calculus.